Hello student. In this lecture, we understand the experiment number 5 to study and analyze the operation of static synchronous compensator. In short, we call as a STATCOM using the Matlab simulation in power system. So the objective of this experiment is to understand the steady state and dynamic performance of the STATCOM phasor model and detail model in the power system. So first we understand the phasor model of the STATCOM. So this is a single line diagram that is available in the Matlab. Same like a SVC, if you search STATCOM in the help in Matlab, you find the detail model and phasor model of the STATCOM. So first understand this phasor model in Matlab. So here you can see that this phasor model is available. So this is an example of STATCOM which is connected at the midpoint of the line with a rating of 500 kV in the transmission line. So you can see that here this is a transmission line of 600 kilometer. Here the one generator of 500 kV which generate the 3000 megawatt 3000 MVA power, and second generator is here which is a 500 kV 2500 MVA capacity, and this is a generator bus B1. This bus B1 to B2 distance is 300 km. Same way this B2 to B3 distance, that is 300 km. So total distance of this transmission line is 600 km. Now you can see that here the STATCOM is connected at the center of or midpoint of the line. It means at bus B2 to maintain the rated value at bus B2. Here at bus B2 load connected is 2 megawatt, and at bus B3 the load connected is 300 megawatt. Same way here at bus B1 load is connected 100 megawatt, and here fault breaker is connected that is used to simulate the fault, and we understand that later on during the fault condition how this STATCOM responds and maintain the voltage regulation in the power system. So first we understand this description of this block. So in the description you can see that the voltage source converter, the STATCOM that regulates the voltage. As we know in the theory that STATCOM regulate the voltage by absorbing or generating the reactive power, and contradictory to the thyristor based static var compensator, STATCOM output current can be controlled independently of the AC system voltage. So as we know that in the SVC, the current is or reactive power is depend upon the square of the system voltage, where here it is not STATCOM, the output current is not depend upon the system voltage. So here this power grid, that is a consist of two 500 kV generators. We already discussed that. This is a 500 kV generator, both the side of different capacity 3000 and 2500 MVA. This is connected with the 600 kilometer transmission line. When STATCOM is not in the operation, when it is not connected at the middle of the line, so at that time the natural power flow on the transmission line is 930 megawatt from bus B1 to B3. It means from bus B1 to B3 power is flowing, which is 930 megawatt when STATCOM is not available in the system. STATCOM is located at the midpoint of the line. It means at bus B2, you can see that it is connected at bus B2. This is the STATCOM block, and that has a rating of plus or minus 100 MVA. It means that can inject or absorb the 100 MVA power. And this STATCOM is a phasor model of a typical 3-level PWM based STATCOM. And if you open the STATCOM dialog box and select the display data, you will see that this data represents this model of STATCOM represents the DC terminal voltage of 40 kV with equivalent capacitance of 375 microfarad, and on the AC side the total equivalent impedance is 0.22 per unit on 100 MVA base. So this impedance represents the transformer leakage reactance and phase reactor of the IGBT. So let's see this parameter which is available in this STATCOM. So if you find out, if you open this model, click on this open model, so you find out the Matlab model of this STATCOM phasor model, and double click on this STATCOM. So you can see that here the rating of the STATCOM is 500 kV, which is operated at 60 Hz, and its capacity is 100 MVA. You can see the 100 raised to 6. So that is 100 MVA capacity. And you can see that the impedance, inductive impedance or inductive reactance is that 0.22. So that represents the leakage impedance as well as the reactor of the IGBT. And DC link voltage, that is 40 kV, because as we know that this is a voltage source converter based STATCOM. So at the DC side that require the DC voltage source. So that DC voltage source magnitude is 40 kV, and the capacitance that stored this 40 kV, that value is 750 microfarad divided by 2. It means that is a 375 microfarad. And you can find out in the controller. So the mode of this STATCOM, select voltage regulation mode. As we know that there are two mode of operation of the STATCOM. One is the VAR control mode or reactive power control mode, and another is the voltage regulation mode. So here we first operate this STATCOM in the voltage regulation mode. So we have selected voltage regulation, and the reference voltage V reference, that is set externally here. So you can externally select the reference at any value. If you want any value like 0.7 reference, 0.9 per unit or 1 per unit reference. So for that you can select the external reference, or also you can deselect this external and automatically that take the 1 per units here, or also you can change the here any reference value for the voltage regulation. So here in this example we set the external reference. So you can see that here the input of the V reference that come from this step block or step state generator. So here we provide the V reference externally. At different time we change the reference value. So you can see that this is a time, and here the magnitude of the reference value which is changing with respect to time. So you can see that t is equal to 0 second. The amplitude of the V reference is set to the 1 per unit. At 0.2 second, the V reference we change from 1 to 0.97 per unit. At 0.4 second, you can see here we change the reference from 0.97 to 1.03 per unit, and at 0.6 second again we set to the 1 per unit. So here we select the external reference. That's why we must be provide the V reference externally. Otherwise you not need this external reference if you select the internal V reference. Then read the next description of this model. So here let's understand the dynamic response of this STATCOM phasor model. So in this model, if you find out if you open this STATCOM dialog blocks, and we see that there is a set at the voltage regulation mode, and that is at the external control reference voltage selected, and with the droop parameter that is 0.03 value. Droop value that represent the droop reactance of the STATCOM. The same like a droop reactance in the SVC we have seen in the VI characteristic. So you can see that here in the controller the droop reactance that is given, that is 0.03, and this is a gain. AC voltage gain is given, proportional gain and integral gain, that is 5 and 1000. Same way DC regulator gain is given, and this current regulator gain. So the response time of the STATCOM that is decided based on this AC regulator gain. We will discuss later on that how this regulator gain changes, the response of the STATCOM is also changes. So first we run this simulation and see that what is the measured value of the bus voltage at the B2 bus, and what is the V reference which is provided externally, and based on the V reference how this STATCOM provide the regulation at bus B2. So let's run this simulation and open this VQ STATCOM scope. So in this scope you can first measure the VM and V reference, and then after QM and Q reference. VM is the actual voltage measured at the bus B2, and V reference is the reference value set externally for the STATCOM that we have put here in the step reference. Then QM that gives the actual reactive power injected or absorbed by the STATCOM, and Q reference that is 0 in this case because we operate this STATCOM in the voltage regulation mode. So there is no Q reference in the voltage regulation mode. If you select the STATCOM in the VAR control mode or reactive power control mode, then and then you can select the Q reference externally, same like V reference. But here in this case, Q reference is set to the 0, but just you can measure the QM based on the injection or absorption of the reactive power to maintain the voltage at the bus B2 near to this V reference value. So here we have run the simulation and let's see the voltage and reactive power. So you can see that this blue line or magnetic line that represent the V reference and this yellow line that represent the actual measured voltage at bus V2. So you can observe that at between 0 to 0.2 second the voltage is 1 per unit, and after 0.2 second you can see that voltage reduces from 1 to 0.97 per unit. So this V reference is set, as you know that in the model here we set at 0.2 second the V reference 0.97 per unit. So based on the V reference, this STATCOM inject or absorb the reactive power. So here you can see that as the V reference is changed, the actual voltage at the bus B2 that is also changed, because STATCOM follow the V reference, because we operate here STATCOM in the voltage regulation mode. So here to decrease the voltage from 1 to 0.97 per unit, we require the absorption of the reactive power from the system. So you can see that here we inject the positive reactive power into the system. It means that we absorb the reactive power from the system to decrease the voltage level from 1 per unit to 0.97 per unit. But here you can see that this voltage, actual voltage measurement, that is not reached to the V reference. That reason is that our droop reactance is 0.03. So because of the droop reactance, we cannot reach up to the V reference value. So if our droop reactance is 0, then our measured value, this yellow line, that reach to this V reference value. Clear? So we will discuss later on that how this droop is affects the output actual voltage measurement. Now let's see that at 0.2 second, after that voltage decreases up to 0.97, so reactive power injecting, and up to this 0.4 second that provide the constant amount of the reactive power and maintain the voltage that near to this 0.98 per unit. Now at 0.4 second, voltage is drastically increases from 0.97 to 1.03, because we set the V reference at 0.4 second 1.03. You can see in this block at 0.4 second we set V reference 1.03. So now your STATCOM try to maintain the voltage at bus B2 near to the 1.03. So for that they require the injection of the reactive power. So you can see that in the simulation waveform at after the 0.4 second the reactive power decreases and becomes negative. So negative reactive power, it means that they inject the reactive power into the system to increase the voltage level near to the V reference. But because of the droop reactance that not reached to the up to the level of 1.03. So that reached nearer to this 1.03. This is around 1.02 per unit value. So you can see that how this STATCOM provide the dynamic response based on the reference value set into the STATCOM. So as the reference value changes, the output voltage generated by the STATCOM is also changes and provide the compensation of required amount to maintain the voltage near to this reference set. Now let's see that how this droop that affects the voltage regulation. So in the STATCOM block, as we know that in this controller block, this droop reactance is given. So if you set this droop reactance to 0 value, it means that your VI characteristic of the STATCOM in the voltage regulation mode that becomes flat. If you see the actual characteristic of the STATCOM from capacitive to inductive mode in the voltage regulation mode, then they have positive slope in this fashion. Clear? But if you set the droop value 0, it means that the voltage regulation mode, this characteristics become flat. It means constant. So now let's see the simulation. Run this simulation for the zero droop, and you can find that you can now see that the voltage is now actual voltage or measured voltage now reached to the V reference, because here we set the droop to the zero value. It means there is no slope in the VI characteristic of the STATCOM, so that you get the perfect voltage regulation based on the V reference set into the STATCOM. So here at 0.97 per unit voltage V reference at 0.2 second. So your measured voltage also reach to the 0.97 per unit voltage after some time. Clear. Same way at 0.4 second also your voltage reference at 1.03 per unit. So your measured voltage also reach to this 1.03 per unit. So this is the effect of droop reactance on the VI characteristic of the STATCOM. Now let's see this. Now let's set this droop again to the 0.03 value. And again run this simulation. So this is a normal condition again. So now second observation, you can see this in the simulation here. The response provided by this STATCOM is very time sluggish. It means the response time of the STATCOM, that takes some time for the reactive power injection to maintain the voltage regulation. So this lack of response provided by the STATCOM, that depends upon the AC voltage gain of the STATCOM. So that is available in this STATCOM block. You can see that here in the controller block, AC voltage regulator gain, that is proportional gain Kp set at 5 value and integral gain that is set at 1000 value. So if you increase this gain, then the response of the STATCOM will increases. So now you observe that the waveform, the complete response you get from the STATCOM in the normal condition at around 0.25 seconds. You can see that constant voltage you get at 0.25 seconds, near to this 0.25 seconds. Clear? So that takes 0.05 seconds to provide the complete compensation, because here you can see that reactive power is increases gradually. Clear? So this time delay, that is depend upon the voltage gain of the STATCOM, AC voltage gain of the STATCOM. If the voltage gain of the STATCOM is higher, then this response time is low. Let's observe this effect. Let's change the gain, AC gain of this STATCOM controller. Suppose I am double this gain, proportional gain take from 5 to 10, and here take the integral gain 2000 and set it value, and now we run the simulation. So now you observe the response time in the simulation. So you can see that the response time is decreases. It means that STATCOM provide the fast response against any change in the voltage reference. So you can now see that STATCOM provide the reactive power absorption in a very short period of time, and they maintain the voltage near to this constant 0.98 at near to this 0.22 seconds. With the previous value of Kp and Ki, they provide the response time after 0.05 second, but with double this gain, that provides the response in half of this time. It means at 0.22 seconds. Clear? So that decrease the response time, half value as compared to the previous time. So this is the effect of proportional gain in the response of the STATCOM, and we also see we have seen that what is the effect of the droop in the voltage regulation of the STATCOM. So this is the two main observation of the STATCOM VI characteristics. Now next we understand that how this STATCOM provide the voltage regulation under fault conditions. So in this case we compare the STATCOM and SVC performance. So here we have the SVC, static wire compensator system. in this simulation model, you can see that this is a SVC power system, same like this STATCOM, same rating of transmission line, same rating of generator, same load, but here we connect the SVC at the middle of the line. So that block is available in this SVC power system. If you double click on this, so you can see that you get the same power system of same capacity, but at the bus B5, middle of the line, middle of the bus, SVC is connected of the same rating plus or minus 100 MVA. So now during the fault condition at bus B4 here in the SVC, we find out that how this SVC provide the response. Same way here also in the STATCOM you can see that at the bus P1 we have provided the fault breaker which creates the faults, and find out that how the STATCOM provide the response to this fault condition. So let's read the description of this condition. So in this condition we compare the STATCOM model with the SVC model which having the same rating plus or minus 100 MVA. If you double click on the SVC power system, then you will see the SVC connected to the power grid similar to the power grid on which our STATCOM is connected. So you can see that same way the SVC is connected in this block, power system block. A remote fault will be simulated on both the system using the fault breaker in series with the fault impedance. So you can now see that here this is a fault breaker in which we have set the switching time at 0.2 second plus 10 by 60. 60 is nothing but operating frequency. Here we operate STATCOM, whole system is operated in the 60 Hz. So it means that this breaker is operate at 0.2 second and then after that is remain on for the 10 cycle of the 60 Hz frequency. But here it is switch off because here we not selected the fault condition. Here we not select the fault in phase A, B, C. If you click on this A, B and C and click OK, at that time they creates the fault condition. Clear? So here we have select this A, B, C and click OK. So that creates the fault on this power system at 0.2 second, and this fault is remaining for the 10 cycle of the 60 Hz frequency. Same thing you can done here in this SVC model. Same fault breaker connected with the fault impedance. Here also same switching time is provided 0.2 second plus 10 by 60. It means that after 0.2 second breaker will close and this fault is remaining for the 10 cycle of the 60 Hz frequency. So to close this breaker, to provide this fault, click on this ABC, mark this and click OK. So at 0.2 second that creates the fault. But if you observe that here in the voltage regulation mode of STATCOM, we set the reference value at different time 0.2, 0.4 and 0.6 second. So to avoid this voltage variation in this fault condition, here we set the time for this, multiply this time block, time parameter of this voltage reference with 100, so that this block will not affect here in our simulations. So now if you run this simulation and if you find out here the scope of voltage and reactive power measurement for SVC and STATCOM, the VM that is gives the actual voltage at bus B2 in the case of STATCOM. In the SVC that gives the voltage at bus B5. Same way QM that gives the actual reactive power injection or absorption at bus B2 in case of STATCOM, and in case of SVC at bus B5 injection or absorption of the reactive power that is provided by the QM. So there are two graphs, VM and QM, you can find out in this scope. The magnetograph or blue line that represent the SVC parameter and the yellow line that represent the STATCOM parameter. So here you can see that the graph of voltage measurement and QM measurement, reactive power measurement. You can see that at 0.2 second fault is created in both the system, SVC as well as STATCOM. So this yellow line that represent the STATCOM voltage, this yellow line that this waveform of yellow line that represents the STATCOM actual voltage measurement at bus B1, and this blue line waveform that shows the actual voltage at bus B5 in the SVC system. Same way here, this represents the reactive power. This blue line that represents the reactive power of the SVC, and this yellow line that represents the reactive power of the STATCOM. So if you observe that here, in the SVC power system, the voltage is reduces below the 0.7 voltage, but in the STATCOM, that is not reduces below the 0.7 voltage. Clear? Same way you can see in the reactive power. The reactive power here injected by this STATCOM, this is the reactive power injected by the STATCOM. This is higher than the reactive power injected by the SVC. This magnetar line, this blue line that represents the reactive power injected by the STATCOM, and this yellow line that represents the reactive power injected by the STATCOM. Why I am saying that reactive power injected? Because here fault condition that decrease the voltage level from 1 per unit to 0.7 volt. So to maintain the voltage near to this 1 per unit, we require the injection of the reactive power. So SVC also inject the reactive power and STATCOM also inject the reactive power. But here the reactive power amount by the STATCOM, which is higher than the amount of reactive power injected by the SVC. That is because of the characteristic difference between SVC and STATCOM, as well as difference in the droop reactance of STATCOM and SVC. So you can see that here the response time provided by the STATCOM is also very fast as compared to the SVC. You can see that here STATCOM provides the very fast reactive power of high magnitude as compared to the reactive power injected by the SVC. You can see here. So if you compare the reactive power injection and voltage regulation, then you can find that the STATCOM provides the better voltage regulation as compared to the SVC. And you can also observe in the waveform of voltage also, during the fault voltage reduction in case of STATCOM power system, that is above the 0.7 per unit, but in case of the SVC, the voltage level decreases below the 0.7. And you can also see that here, after injecting this reactive power into the system, the STATCOM system set the reference value voltage, set the bus voltage value at near to this 1 per unit or exactly at 1 per unit before the SVC maintain the voltage at 1 per unit. You can see that SVC maintain the 1 per unit at this time, but STATCOM that maintain the voltage at 0.4 seconds. So that is because of the response time provided by the STATCOM. Okay. So you can see that after 10 cycles, when fault is clear in this duration, this is the 10 cycle period, after this 0.2 second, when fault is clear, again your voltage is set to the reference value. So you can see that the reactive power injected by the STATCOM is drastically reduces and becomes zero, so that again your reference your bus voltage that is set near to this 1 per unit, very fast as compared to this SVC. You can see that the SVC response during the regains during the normal condition is also that provide the very slow response and maintain the 1 per unit voltage after taking some time. So you can see the difference between the voltage regulation provided by the STATCOM and SVC. So this is the comparison of STATCOM and SVC during the fault condition. Now you can write this point also in the comparison of SVC and STATCOM. How this STATCOM provide the fast response? What is the reason behind this? So this is a phasor model description of the STATCOM. Next we discuss the detailed model of the STATCOM. So if you search the STATCOM detailed model or just search the STATCOM, you find out the different STATCOM model available in the Matlab. So first is this is a GTO based STATCOM available. Second, we have right now see this STATCOM phasor model, and the third one is the STATCOM detail model. So open this detail model and click on this open model. So you can find out the Matlab simulation of this detail model of this STATCOM. Now the same like a SVC, here in the programmable voltage source, it is programmed to create the voltage sag or voltage swell condition. So you can see that in the programmable voltage source, the amplitude value at 0 second, that is set to the 1 per unit, and at 0.1 second, that is set at 0.1 second, that is set to the 0.955 per unit. It means the voltage is reduces. So at that time, what will happen? The STATCOM inject the reactive power to maintain the voltage near to this 1 per unit. Here in this detailed model, our reference voltage is fixed, that is 1 per unit. Here voltage sag and voltage swell condition that is generated by this three-phase programmable voltage source, that is act as a generator. So here initially at 0 second voltage is 1 per unit. At 0.17 second or 0.1 second, the voltage is reduces to the 0.955. It means that is below the reference value. So at that time, STATCOM act as a capacitive mode and inject the reactive power into the system to maintain the voltage near to the 1 per unit. Exactly opposite, you can see that at 0.2 second, voltage is increases to the 1.045. It means above the reference value. So at that time, the STATCOM requires the absorption of the excess reactive power from the system to maintain the voltage near to this 1 per unit. And at 0.3 second, the voltage again set to the 1 per unit. So let's see the observation of the waveform. Now you can see that this is a STATCOM, and this is a STATCOM pulse generator or STATCOM controller available, which is generate the gate pulses for the STATCOM block. You can see that here this is a 48 pulse voltage source converters, and this is a 3-level bridge type of diode claim converter, and that is connected through the zigzag transformer with the phase shifting. And you can see that 7.5 degree phase shift is provided because it has 48 pulse voltage source converter. So we require the 4 3-level diode base bridge converters, which generates the output voltage, which is more near to the sine wave, because here we use the multi-level converters, 48 pulse. As we see in the theory that as you increase the number of level or number of pulses, the output voltage of the voltage source converter becomes more and more near to the sine wave, so that the harmonic content in the output voltage is less. So your STATCOM inject the less harmonic into the power system, so you require the small size of the filter to filter out these harmonics. So this is the STATCOM voltage source converter, and this block STATCOM controller generate the gate pulse for all these thyristors of the voltage source multi-level converters. So you can see that the input of this STATCOM controller is a 3-phase voltage VABC IABC, and that converts this VABC and IABC into the PQ quantity, and another input is given to this measurement system, that is frequency and angle, through this PLL block. So this phase lock loop block that is used to synchronize the output voltage of the voltage source converter with the power system voltage. Then and then you can inject the voltage into the power system in synchronization. So here this omega t and frequency that is given through this PLL block to this measurement system. So there are 4 input to this measurement system. One is VABC, IABC, frequency and omega t. Then after you can see the output of this measurement system, that is a V measurement. Then PQ, it means active and reactive power. Then IQ, that is the reactive component of the current, that is the average reactive component of the current. ID, that it is a direct axis component, that is called as a active component of the current. We are not going into detail about all these parameters, but just remember that IQ, that is a reactive component of the currents, that is responsible for the reactive power injection, and ID, that is a real power, that is a real current, real part of the current, and that is responsible for injection or absorption of the real power from the system or to the system. Now this is a voltage regulator, voltage regulation block. So you can see that there are two inputs. One is a V reference, that is generally set at 1 per unit, and V measurement value, that we measured from this measurement system based on the actual VABC and IABC. So based on the difference between V reference and actual voltage measurement, that generate the IQ reference. So that IQ reference, that is nothing but a reactive component of the current. So this reactive component of the current, that is responsible for the generation of the reactive power into the system. So based on the value of IQ reference, your STATCOM inject or absorb the reactive power from the system. And you can see that the same IQ reference, after this limit computation selection switch applied to this current regulator block, and one IQ that you got from this measurement system. So that is IQ is the actual measurement, actual reactive power component of the current, and IQ reference, that is a reference set by this voltage regulator board to maintain the voltage regulation at the load bus. So based on the difference between IQ reference and actual value of the IQ, this current regulator block that generates the alpha, that is nothing but a firing angle at which your thyristor is fired. So output of this current regulator block, that is applied to the firing pulse generator block. So you can see that here this output is applied to this firing pulse generator block. Then sigma, that is given after subtracting the phase shifting between the two converters. You know that in the multi-level converter, between the two converter we provide the 7.5 degree of phase shifting, so that you get the staircase type of the output waveform. So here 7.5 degree subtracted from the 180 degree, so that sigma is provided. Then omega t, that you got from the PLL block, so that you provide the synchronized pulses. And then after output voltage provided by this voltage source converter, that is also synchronized with the power system. So this D alpha, that is nothing but the alpha degree that is required to maintain the DC voltage at the input side of the voltage regulator. As we learned on the theory that the voltage regulator, voltage source converter at the input side, we provide the DC source. So to maintain this DC source to the constant value, we require the real power flow from the power system. So how much amount of the real power flow from the power system to STATCOM? So that is decided based on the D alpha. So this D alpha is provided as an input to the firing pulse generator. So based on that, the output voltage of the voltage source converter, that creates the phase angle difference between the power system voltage and output voltage of this VSC or voltage source converter. So based on the requirement, the real power is flow from power system to the STATCOM, and to maintain the DC link bus voltage to the required value. So all these four parameters that generate the firing pulse for all the thyristor of the 48 pulse 3-level multipulse converter, and this pulse, you can see that this output of this STATCOM controller, that is applied to this STATCOM block. And you can see that in the STATCOM block here we have all the pulses now distribute to this all these 3-level bridge converters, and based on that generate the output voltage ABC, and this ABC that injected into this bus B1, so that provide the voltage compensation. Now let's run this simulation here and find out that how this STATCOM provide the compensation against the voltage disturbance. The voltage disturbance we have created by this programmable voltage source. So in this programmable voltage source, you can see that 0.1 second voltage is reduces at 0.955 value. So at this time, this STATCOM inject the reactive power. So let's see this graph of this different parameter of the STATCOM. So VA secondary, that is the secondary side voltage of this STATCOM. It means that is the output voltage of the voltage source converters. Then VA voltage, that is the primary voltage, and IA primary, that is the current injected by this STATCOM. So there are three quantity measured here. This red line, that is represent the current. Then this blue and yellow, you can see that both are overlap with each other. That represent the secondary voltage and primary voltage. Here we take the 1:1 transformation ratio. So that's why both the voltage are same value. Now we can see that this is a reactive power injected or absorbed by this STATCOM, and this line that represents the actual voltage at the bus and the V reference. You can see that this magnetar line or blue line, this represents the V reference value, which is set at 1 per unit, and this yellow line that represents the actual voltage at which the STATCOM is connected. Means this is the voltage at the bus B1 here where the STATCOM is connected. So let's see this, analyze this graph here, and the last one, that is the DC voltage of the STATCOM, that is the input voltage of the STATCOM, that is available here. You can see that this is the input DC voltage which is provided to this multipulse converter, 48 pulse multi-level converters. So now observe this waveform at different time. You can see that 0.1 second our voltage is reduces. You can see that. Why? Because in the programmable voltage source we set this value to the 0.955 per unit at 0.1 second, so that at this bus voltage also reduces because this bus is near to this generator, so that you can see that voltage reduces to the 0.955 value here, and at that time you can see that reactive power injected by this STATCOM. So by the injection of the reactive power into the system, they can maintain the voltage near to this 1 per unit. So now at the same time you can see that DC link voltage also increases. It means that the STATCOM absorb the reactive power from the system to maintain the DC voltage to its rated value. At the same way you can see that here at 0.2 second voltage is increases to the level 1.05 per unit. So you can see also in the simulation here at 0.2 second the voltage is increases drastically up to the 1.03 per unit. So at the same time also the reactive power now absorbed by the STATCOM, because now voltage is increased above the rated value. So to absorb the excess reactive power from the system by the STATCOM to maintain the voltage near to this rated value. So you can see that here the voltage after the compensation that decreases below the 1.03, but it not reach to the exact 1 per unit. The reason is that because of this proportional gain provided by this or proportional droop characteristics provided by this STATCOM. You can see that the voltage is drastically reduces and set to the one level, but that is below the 1.03 per unit. And after that you can see that 0.3 second again the voltage is set to the 1 per unit. So after that reactive power injection or absorption by this STATCOM becomes 0 after some time, and you can see that voltage now again set to this 1 per unit. So this is all about the detailed model of the STATCOM. Same like a phasor model, this model also provides the dynamic compensation against any voltage variations in the system. So I hope you understand this detailed model as well as phasor model of the STATCOM. If you have any doubt, then you can ask me the query regarding these simulations. So after that, watching this video, you write the conclusion in this experiment.